Well, good afternoon and welcome to talks. During semesters when classes are in session, we have this talk series which happens every Tuesday at 1:30. We've had speakers from Park, and Xerox, Stanford, CMU, and sometimes from entrepreneurial people as well. And the thing to know is that you can ask questions at any time. The microphones in front of you should have their green light on. They're not working. That button doesn't work. So if you push, oh, there it is. Okay. So if you push, if you rattle keys on the table, we will hear it. But basically, we're recording this, and hopefully it'll be useful for people to come and listen to this talk in the future. Today's speaker comes to us from Paris, where he runs a company that thinks about how to program for parallelism, and also he has been involved in research and running and directing research, even in funding research in the mobile space to very broad areas. So he will be telling us about how his perspectives have given him this language that I think is very exciting and very timely. And without further ado, I guess the first thing I want to say is that he'll be, the talk will be over at 2:25 when we'll go out and have a little bit of sodas and cookies to meet each other. But in the meantime, Pierre, please come and give the talk, and we look forward to what you have to say.
Thank you, Ted. So good afternoon, everybody. I would like to introduce some works we are going to develop at HPC project. Mainly, we are dealing with a new generation of chipsets called accelerators, working to be able to tremendously accelerate computation. The company by itself is focused on real-time simulation. What we try to do is to be able to integrate a different kind of modeling tools for people to be able to analyze systems, train themselves on these systems, and in fact take into account physical behavior of the environment while they are operating their systems. So mainly what we have to do to achieve this kind of performance is working, of course, on the implementation of these algorithms, but also at the numerical methods and the underlying modeling tools for achieving this kind of real-time and interactive simulation on real physical representation. So for us, computing is a tool, and we, at the center of our platforms, is a compiler able to produce very optimized parallel code. And my talk will be focused on the work done on this platform. So I would like first to express what we think is really difficulties with the present situation with parallelism, and some wrong ways to address this kind of problem, things we try to not do, and the way we go around the current situation where people want to have very high performance using parallel chipsets, but in fact get slower code. So we try to address the problem of scalability. And I would try to define what I think is scalability, why it is important. After that, I will talk about some problem facing ISVs in the real life, in the real economic life, where people have to manage sometimes very long-term projects with legacy code that is important in their project. And I will finish by a summary of what kind of development we do, which directions we explore today to get better results. So the problem with parallel computing is an old one, because mainly each time you have order and you have to maintain order in the execution of a program, you destroy parallel, because order is the contrary of parallel execution. But in fact we are taught to think about algorithm as a sequence of operation to achieve a result. So by nature, the way we express programs is sequential and is ordered. And of course, when you want to have people beginning to think in parallel, you confront this situation. So first, you have to, in fact, go back from the basic education of a computer scientist and tell them how to detect partial ordering, so how they could change the order of the algorithm without changing the meaning of what they want to achieve. Also detect that there is at a certain level, some operations that don't have order at all. So you could organize the way you want the operations. So mainly you could operate them directly in parallel. And when I mean that, I mean also that you may be in a position to ask everybody to do the same operation on different data and get the result you want to have. That is an operation that is by itself a large-scale parallel. And of course, you run rapidly into a problem, which is there is no evidently way to express your program. Every language we have today comes from the background of sequential programming, and you don't have a natural way to express your program to run it in parallel. So each time you see a program that is designed with explicit parallel in it, you've got something that is a sequential program, and you have to add some either structure or construct to make it parallel. To begin with, we have worked with concurrency from a long time ago. Concurrent system comes from concurrent execution, for example, in operating systems. And of course, it's already a complex subject because you have race condition. You have to manage the way you access some shared data in the system. And some solutions have been built to address these problems, like lock, semaphores. Functional programming is a way to solve this by not sharing anything. But concurrency is not parallelism. I mean, when you have a solution for correct concurrent execution, in fact, you destroy parallelism. Why? Because you enforce an order. So mainly concurrency provides you some tools to enforce the order of execution, but you have not dealt with the parallel execution by doing that. You have simply solved the problem of correct execution of your program. So sometimes we run into trouble with customers that told us they have already a parallel program. In fact, what they have done is mainly to have a multi-threaded program with a lot of shared data structure, and they have added to their program a lot of lock and critical section protection to make the program run correctly in parallel. But that's not an efficient way to address parallelism. In fact, what they see sometimes when they try to add more resources in their system, the program is in fact slowing down because the cost for the lock and the semaphores grow at the same in a linear way with the number of resources they want to share. So first is we want to I would like to stress the fact that solution for correct concurrent execution is not a solution for parallelism. And a lot of time, people mix the fact that they have, in fact, the correct execution in parallel and the fact that they are really redeveloped a parallel solution for the problem. Of course, not sharing is better. You don't pay for synchronization, and it was in the past a very good way to achieve large-scale performance on AMI-MD architecture. But functional programming is mainly dealing with control-oriented parallelism. And that's the trouble with, in fact, the way we develop programs. Everything we have in language deals mainly with the control of execution, the control path of this execution. So each time we try to use a well-known language to deal with parallelism, what we do, in fact, is mainly dealing with which tasks can be run in parallel at the same time without mixing with the ordering of the access of the data. And that's something that functional programming is very good to organize. We know quite well that Lisp was used several times for MIMD program development. Also, we have stream computing that is has gained some success more recently. But people working on real applications have shown that, in fact, you get at most 3 to, let's say, 5 concurrent threads in a usual application that could be run in parallel. So inherently, the scale of parallelism you could achieve by control-oriented parallelism is limited. And that's something that is really a problem when you want to go beyond, in fact, the current generation of multi-core CPUs. So at the same time, you have the fact that people are not that much more dealing today with functional programming. You don't have that much people trained to do that, and people are much more proficient in C++ or Java or imperative programming in general. And secondly, when you want to organize only control-oriented parallelism, you run into a wall, which is the fact that after 5 threads, you can't find any more parallel inside the application. So what we try to do at HPC project is really working on scalability. Scalability in the application, scalability in the way we program the architecture, and of course we try to balance the kind of architecture we work on to look at the way they could be programmed to maintain the scalability. So by scalability, I mean that the more you put computer resource for dealing with your application, if you scale at the same time the number of data you put in your problem, you get the same execution time at the end of the day. So that means that, in fact, if you want this kind of behavior, the way you address parallelism should be data-oriented, data-driven. That means also that your application is data-dependent. With different set of data, you may have different behavior. And today, one of the problems with the way you express an application is that you don't really deal with this kind of information about the data set. What you do is mainly organizing the control flow of the application depending on certain value of the data, but not the size of the data, for example, gives you different way to organize your execution. Also, a problem with that is that your memory hierarchy become a central piece of your performance. Today, when we deal with accelerators, the main problem is not computing power. Computing power is for free. You have all you want in the current generation of CPU. The real trouble comes from the fact that you have to move around the data inside the architecture. And if you don't organize by programming this organization of the data behavior, you don't get your performance, because at each level of your architecture, you get some limitation, especially, for example, for the GPU generation of computer. Today, the real trouble comes from the connection between the main memory and the onboard memory, dealing with the E3 connection, PCI Express connection in between. But in fact, when you are on the board, you have achieved really the more difficult part of your programming. Of course, when you deal with bandwidth, you don't have to only think to raw bandwidth on the system. Sometimes you have to look around of the way the addresses are generated in the system, because in fact, at the end of the day, what is useful is how much data you are able to fetch in your memory. And some part of this fetching mechanism comes from the fact that you have to compute, for example, addresses to be able to organize the information before sending it to a special memory. In particular, for example, in the current generation of GPU, you don't have the kind of scatter gather we have with vector machines, and a lot of problems we have with managing the development of application for GPU comes from the fact that when you don't deal with very aligned data structure, the performance of data access is slowly is going down dramatically, because you go from parallel access to the memory to a linearized way to access data. So mainly you have lost everything when you are not in a situation to align data. So as I have said, in that specific project, we want to focus on data parallelism. So the way we see today the trend in computer architecture, there will be a lot of benefits to reap off a comeback to algorithms and the way to express these algorithms to take advantage of regular structure of computation. This model of information comes from the SIMD kind of architecture. So the way to address that is usually you have to think about your computer as a machine with a single instruction unit able to distribute an instruction to be done to several core CPU, and this CPU each executes this instruction on their local data. That's something that is very powerful if we regard the way to use the silicon on the chipset, because you minimize the control size of the chipset, and for a very small part of the silicon used to decode the instruction, you get a maximum throughput for computation. So still the problem is how we address this kind of organization of computation. Today we have several ways to deal with that. We see people providing new instruction sets. For example, you have CUDA or OpenCL, which extends some C++ code. You could have pragmas, such as, for example, OpenMP, which are mainly a way to put metadata around your program to give more information about the way you want data processed. Or you could have a kind of magical way to structure information with inherently parallel way to deal with it, like something TBB, for example, building block, that in fact puts the organization of parallelism under the cover of the runtime in the data type. The real problem with that is you don't have a way to standardize things. Everybody comes with new ideas. Each time we run into the problem to change a program and adapt it to this new way to express the problem. And in fact, the real trouble with this approach is that we don't have a standardized way to organize the manipulation of data. We are used to have a control set of operation in language. We are not used to map, for example, an array. And array is the best organization we are able to describe in just one instruction. When you deal with, for example, linked list, you have to organize everything by hand, and you don't have this kind of meta structure representation of information that could be dealt with a lower level runtime, for example, to adapt the data and map the data on the architecture. In fact, that comes from the fact that in an usual computer, when we this part of the processing of dealing with data is either dealt with by the compiler. When we look at, for example, register allocation, that has been a very strong field of research for compilers. We don't have anymore to tell which variable should be in a register. It's totally organized and automated by the compiler. And the model of organization of the data space is uniform. We don't make any difference between in allocation between part of the memory. Cache also has something that run automatically and has some take advantage of some hypothesis in the way the code is behaving. But when you have codes that are well fitted for data parallelism, in fact, it appears that the hypothesis for cache work is not valid anymore, because most of the time you go through large sweep in the whole data space that don't fit anymore in the cache volume, and when you run loops over this large data space, in fact, you keep thrashing your cache, and you really have to have better strategy to organize your data than having only this uniform address space. You should be cache aware in the way you organize your data access. Also, one of the problems, for example, for multi-core CPU today is that, in fact, you are very competitive in the way you use resources. Each time you want to address something, you send an exception and you try to grab and keep the resource for the thread running. And we well know that when you reach the limit of the resource available in the architecture, having this kind of very competitive behavior just crash down the mechanism of allocation of resource. That's the way, for example, when you have an Ethernet medium and you have a lot of body wanting to talk on it, you just simply get less and less possibility to talk on the boundary. In fact, when we look at a very old way to organize computation on parallel architecture in the 80s, for example, you see that, in fact, a lot of work has been done in this time to just try to make cooperative use of resources. For example, a lot of people have worked on banking strategy of dealing with interconnection network to maximize the interrelationship of part of the program for them to coordinate in the use of the memory, in the use of the network, to be able to just scale, because everybody has a strategy to share intelligently, cleverly the resources inside a program. Today we have the same situation, in fact. Of course, we have no more banks, but we still have several ports on an, for example, new generation Intel chipset. And the way you assign your data in the banks of memory look like a banking strategy for a Cray computer. So you don't get the same performance if everybody is located on the same part of the memory, or if it's distributed to benefit from the additional bandwidth provided by the several ports. For more complex chipsets, we still have the necessity to share buses, or you have a generation now coming with network on-chip capacity. To use this kind of chips, of course, you can't have a very automated way to use a network. You should be able to have particular algorithm just to organize the way the data is transferred from one part of the circuit to another part of the circuit. For example, we are working today on Pierre chipset. I don't know if you're aware of that. That's a chipset made mainly for embedded telecom architecture. But they have a very interesting on-chip system, which is really oriented to maximize input-output bandwidth. So for any kind of stream computing application, it's very well suited. But in fact, you could choose between 5 networking strategy on chip. And of course, the choice has very strong consequences on the performance you get from the chipset. To do that, you should be able, in the design of your, at the level of the design of your algorithm, to take into account the topology of the mechanism of networking. And today, it's something that could not be expressed at the same time in an application. So when you try to deal with all this problem, an usual way for a programmer is to come with a new kind of language. This is not really a solution, because when you develop a language that is too much targeted to an architecture, you run into two kind of problems. First, the decision to switch development of an application on this language is a very strong one, because you know that when you have made this decision, you will have to be consistent with it for a long time. And that's, for a manager, it's a decision that could be of consequences if the project is not working because the choice has not been efficient, or the solution has disappeared because the company proposing this language has disappeared. So that's not very very easy to do. For developers, it's also a choice very difficult to do, because of course you have to become proficient with this language. So you have to get involved in a lot of tutorial training, etc. And that's not easily done if you want to attain a certain level of performance. So at the same time, you see another situation that is an ISV. It's a rule for them. You don't want to have one application with several codes describing this application. Every company, every ISV who has tried to maintain several source code for the same application has failed. It's too much work. You can't have the same bug level solving in each version. You run into trouble between versions. So usually people and industrial companies want to have only one code and have it maintained, and maybe compile and compile workflow for compilation that is dedicated to particular situation, but only one source code. So what we try to do is to have something that is able to give good performances, maintain one trunk code only, be easy to learn, and not be trouble for a manager to decide to go this way, and practically give you results in quick time. Of course, at the same time, it could provide some back information about the best way to use it better, but at the beginning, it's not necessary. So what we try to do today is to couple different kind of open source platforms to give this kind of smooth workflow from a high-level description of a program that has not to be particularly oriented toward a kind of parallelism or a particular solution, and make as much automated as possible the transformation from this description to an optimized version of the code toward an architecture. And of course, for us, it's something that we use to maintain a versatile version of our simulation environment. So at the central part for what we do is something that is a compiler, source-to-source compiler, able to, in fact, analyze any kind of sequential program, either in Fortran or C, and produce something that is an abstract version of this program. This abstract version, I come back to it, is mainly something that describes data sets that are targeted by instructions. When we have this kind of operation of information, we are able to transform the program and make it more prone to parallelism, and at the end to simply produce a new version of the source with implicit instruction for dealing with parallelism in it. We could address today two kinds of parallel expression of the program. One is OpenMP, the other one is CUDA. An OpenCL version of it is under development. As you should note, we have not worked that much on distributed memory system today. Why? Because currently we think that the MPI version of dealing with communication with this kind of architecture is not very easy to deal with due to the very low level instructions that are provided by the library. So if I look at the main mechanism of Par4, what you have is we in fact go to through instructions and put with each instruction pre and post condition that are a formal representation of the way the instruction impacts some data. Of course, it would not be efficient to just have an enumerative list of data manipulated by an instruction. So we use something that is a polyhedral representation of the data dealt with the instruction. By polyhedral, I mean that you have mainly inequations that describe a polyhedra in the data space with indexes that are involved in the loop or in the parallel instruction that is analyzed by the compiler. One important thing is that we don't do that only at the instruction level, but we are able to address a hierarchical representation of these data sets to be able to analyze the situation at the block level, at the function level, and in fact also between instruction calls. So we track each callee sites to be able to understand which kind of dependencies are present when a call is situated in a certain part of the program and calls the function. The fact that we have this tracking of the dependencies makes us available to change the ordering of the instruction while maintaining the semantic of the program at the same time. So we are able to, after this first analysis, to restructure the code to expose different kind of parallelism and work either on coarse-grained parallelism on the outer loop of the program or very low-level fine-tuning parallelism if we work more in the inner loop of the program. So for accelerator, mainly the real trick is to restructure the inner loop and try to maintain a good level of locality in the work done in the coarse loop, because you don't want to move back and forward between the memory of the accelerator and the main memory. So you try to put as much work as possible on the data you have already uploaded in the accelerator. Of course, you can't go too much in this direction because your instruction cache on the current generation of GPU, for example, is limited. So if you put too much instruction in your outer loop, you just thrash the instruction cache, and again, you get into trouble. So the production phase today in Par4 is very heuristic oriented, because we have for each generation of chipset, in fact, measure directly on the architecture some parameters to understand which kind of optimization is better suited for this kind of organization of the computing. I don't think that would be possible to automate this part, but the fact that the program is written to be analyzed by Par4 make this kind of work available for any program that is analyzable by the front-end compiler. So today, not any kind of program could be analyzed. Here I have put an example where on the left side, you've got something that is very usually written by the C programmer who want to allocate an array. The trouble is, I have no information, in fact, that you want an array here. You just have a non-typed space of memory allocated. And my compiler should be in a position after the allocation to track the fact that through the use of the indexing, I partition, in fact, this large space in cell of a certain type. In fact, when you look at C99, you have another way to allocate the memory. A way which is very clean concerning the way you describe the type of the components of the array. In this case today, we are not able to get the right kind of information to manage the array here. We still are working on an automated deduction for this kind of link between the two instructions. With this kind of information, we get directly the same kind of information we could have get from a Fortran 77 program, for example. So it's directly manageable today by the compiler. This problem with the kind of writing style, in fact, we run into, give us the idea to go back one step further and don't ask anymore the programmer to really express things in very low-level sequential language. So we are working today with Scilab, which is mainly a competitor of MATLAB, to use two kinds of organization of program. One is quite Simulink-like. If you know it, it's mainly an operator language when you have boxes and you connect boxes in a data flow way to describe the overall application. But each box could be could contain much more, I would say, vector-like operations that are described in linear algebra scripting language. Mixing the both approach, we think that we have something that is quite able to capture at the same time control level parallelism and data parallel operators. Of course, we are limited to matrix and arrays, but as of today, I would say that's the kind of information anyway you use a lot to describe your parallel applications. So we ask people just to develop, as usual, in this kind of scripting language. What we do is mainly we have worked a lot on the semantic definition of the scripting language. Because today, in fact, it's inspired from MATLAB. MATLAB has no real semantic definition. So when you write a compiler with a language with no cleanly defined semantic, it's really difficult. So we have restricted the language to get something that is a clean definition of semantics. And on the first part, we transform this high-level language, scripting language, to a low-level parallel, not parallel in the first step, but a cleanly written intermediate language. When I talk about cleanly written, as I mentioned, we write the C code, for example, to describe correctly the kind of type we are able to deal with to parallelize the code after that. So in the second step, from this clean implementation in low-level code, we are able to produce a parallel code. Something that we would like to develop further is the connection between this kind of static approach to parallel code production with runtime. In fact, runtime is a strong trend in software engineering for years. We have C++, we have virtual machine. Today we have managed code with C#, for example, or Java. But we still have some real crazy features that are not working, even in today's language. For example, I give that, it's an example coming from a very good book on C++. You see that I have a type that inherits from a global type to array. In fact, when I describe a method for the array, I try to go through the array and iterate over the elements. But if I call this function with more2array, it's not working. Why it's not working? Because in fact, the compiler is inferring that the size of the elements are defined here in tuarray. If I change the type of elements here in non-tuarray, I change, in fact, the size of the allocation. And as I am I'm doing pointer arithmetics in my iteration, it's not working anymore. And this kind of situation you see a lot when you try to mix implicit data allocation you get from C, for example, and more modern way to deal with type as in, and especially when you have dynamic typing as in C++. So we think that today a good direction to go further in working for parallel production is to work on a better interaction between what I've shown you as a static way to address code production and the way to deal dynamically with type. Because why today I can't deal with C++? I can deal with C++ because in Fortran 77 everything is very, very, very static. I have no dynamic memory. My type is what they are, and everything is known at compile time. So I'm able to run very strong optimization at this level. C++ is nearly intractable because at compile time, sometimes I don't even know which kind of function will be called really in the program. we think that something should be done. That's open research for us today. And the first thing we are working on is something with an area team in France. We have designed a runtime for scheduling operators. So mainly what you have to do is to provide several implementation of an operator to the runtime. And the scheduler is able to cooperatively manage resources to optimize the allocation of these resources during the execution, allocating the operator on either, for example, a multi-core, several core on a multi-core CPU, or an accelerator is one is available, and the operators are also available in the right instruction format for this accelerator. So this runtime is called SARPU, and we are in a common project to, in fact, interconnect PAR4, and especially the Simlink part of PAR4 to the SARPU environment. So I will stop here. Right at time. I don't know if you have any question. I'm sorry, I should have run an example. We have some nice example of computation with fractals today and our CFD, computational fluid dynamics with this environment. But my computer is a very small one for travel, and I have not
There's nothing on the web you can bring up?
we could send you some links of YouTube videos.
So maybe there's a YouTube you could bring up?
Just now, I'm not sure I remember. No, I don't have the link. Sorry.
So it's a very important area, and especially for this university, we are extremely excited about computer engineering. In fact, it is the basis of our curriculum. I'm sorry that the master students didn't take advantage of that today, but I'm sure that they will want to watch this tape. We had 9 people watching online, so there's more people online than in the room, and so I'm really happy about that. I've asked them if they want to ask a question as well, and I guess what I want to ask is, you're an expert at this, okay? Now, for us learning about how to program in parallelism, do you think that the on-ramp for learning it is going to improve dramatically over the next 10 years, or do you think that programming the parallelism is really a mindset, and you're going to have to understand all this machinery, as deeply as ever?
I think there is 3 levels. The first one is algorithmics. That's something that really only must be learned to think of the way to organize problem-solving algorithm in parallel. That's something that must be learned. We are not used to do that, and today that's only man that can produce this kind of information. The second level is parallel programming. I really think that today's parallel language are either too strongly linked with architecture or poorly designed. And really, I think that there should be some work just to alleviate that. And it's part of the work that must be done in the software engineering part of the research. The third part is understanding the way the architecture is working at the hardware side. And really, I don't think that's something that should be put exposed to the programmer, because today you don't program in binary RISC CPU. So why programming in parallel at the level?
So I have a question over here.
Yes.
Do I need to push the button? No, doesn't look like it. Very good. So my question is the following. I liked your observation about the data-oriented nature of parallelism going forward. I come more from the software side of the house, so to speak, and in particular from the AI side of the house and databases. And there we have been talking about things like Blackboard systems, forward chaining, deductive databases, more recently about things like Hadoop. And all of these are, you know, at least more or less data driven as opposed to control driven. So my fear is that kind of the parallel computing world keeps on pushing on, you know, C++ and creates, you know, a C++ based on C++ that stays very control oriented and doesn't kind of learn from all the, you know, I agree there probably hasn't been enough work in this area, but it seems like there should be more push in this data, taking advantage of what people have done in the past. And I just wonder what your perspective is on those things.
That's why I think that the solution is not pushing a new intermediate level language, because you have to compare them with the millions of people who have learned Java and C++. So you can't do that. The only way to, I guess, to speed up things is to speed up the application development cycle. Because today, why people are working with this kind of environment, because they know them, they are quite efficient to program. And for them, it's easier to go this way, to learn a new fancy language, better suited for data parallelism. But if you are able to come with something that is more efficient even to produce C++, and that's why I target MATLAB, for example, today, because you see that not expert programmers like MATLAB. Why? Because they just come with what they used to write on the paper for math and just punctuate it, and it's working. So that's increase their productivity a lot. So changing the level of representation for program for me at the same time is the right thing to do, because that's the algorithmic level, and that's there is a more work to be done by experts, because that's the way we could expose the maximum of parallelism. And just keep the C++ level for experts. So if you are a current programmer, you just write the high-level representation inherently parallel, and you let the compile things just do their job. You don't care about if they go through C++, C, don't know, because you don't care of the instruction set of your computer today.
So it sounds like you're more, you know, open to new programming languages, or instead of, say, augmenting C++,
yeah,
or creating a new version of C++, or enhance C++, if you will.
Yeah, yeah. My thinking goes to the fact that everything coming from C is control oriented. You can't go against that. The program has been created to organize the flow of computation. So your control flow oriented. You can't describe to the mapping of data with this kind of language. Or what should be done to get efficient data parallel execution is data mapping. That's geometry. And you don't have a geometric language to program today. Hadoop is the right direction, because what I like with Hadoop is the fact that your control flow is totally data oriented. You put the data and the flow goes to find your data. And I think that's a very interesting way to go.
We had another question back row behind. You had a question? Oh, okay. Deal with it.
I have a question.
Go ahead,
I have a
please.
question. So I hear you were advocating asynchronous data flow and data-driven computation. Have you considered any provisions for lazy evaluation and other forms of on-demand computation?
Okay. We have considered lazy evaluation as something very important for dealing with scripting language, because the problem we have with scripting language is the fact that as you deal with something that has been interpreted, the dynamic structure, the way people think and program in these things makes the decision of typing kind of changing in time. So lazy evaluation is very interesting for that.
Yes.
So we have introduced some a version that is currently not the production version, but we have a version using lazy evaluation to give more polymorphic behavior inside the language. In fact, we use today a kind of ML kind of type inference in the program, but it's static. So once you have decided the type, you don't go and reconsider your choice. With lazy evaluation, we would like to have this kind of behavior. The problem with that is that when you do that, if you don't have the corresponding runtime to change your optimization when you have decided to change the type, you have done nothing. So we lack this part.
I want to go back to one of those points you made earlier. In terms of getting the algorithmics, parallelism, and connection of the hardware together with those 3, how do we maybe change the way we teach it to students? Because it's been a very, very difficult thing for people to grasp how they can deal with this. And they, they throw up their arms, or they just right to the metal. They say, I'm going to be a GPU programmer. So what's in between?
I guess people focus too much today on fancy architecture. That's low. That's not future-proof information, because each generation of chipsets just provide new kind of inputs to that. What I think is that, I don't know, but in France, the thing I have seen is that people don't learn any more algorithms. So they don't learn data structuring. They just go learn a new language, and the next one, and the next one, and the next one. And they are very happy to put on their resume the number of languages they know. I don't care. If you are a very experienced programmer, you can learn a language in months, in 3 months. What I need to know is they know how to structure data to be efficient, depending on what they want to achieve at the end of the application. And I think today things like that seems boring. But for me, it's a better way to address the problem.
I totally agree. I think that's a really great way to end it. I think it's a fantastic statement. I think all the students need to think about that. And why don't everybody just join me and you